Alright, last problem in this batch of exercises. Let m be the ideal. These are ideals in polynomial, integer polynomials in one variable. I don't know why we chose t here rather than x. But let m be the ideal generated by 2 and t, and a be the ideal generated by 4 and t. I'm going to prove that a is primary, the radical of a is m, and a is not equal to m to the n for any natural number n. So why did we choose m for this? Well, it turns out you can prove that m is maximal. And to prove that, well, if you take the polynomial ring and you quotient out by the ideal generated by 2 and t, well, when you quotient out by t, then you just get z. And when you quotient out by 2, you get z mod 2z, I guess. So you get this quotient, and so this quotient is z mod 2z, and z mod 2z is a field, and so therefore, when you quotient, if quotienting a ring by an ideal is a field if and only if what you quotiented by is a maximal ideal. So therefore, 2 comma t, this ideal m is maximal. So we want to prove, the next thing we're going to prove is that the radical of a is equal to m. So radical of a is not equal to a, since if the radical of a is equal to a, then 1 is contained in the radical of a, meaning that some power of 1 is equal to a, which means that 1 is equal to a. No, some power of 1 is in a, which means that 1 is in a, which cannot be true since a is not equal to all of z adjoint t. So therefore, by maximality, we know that the radical of a, the radical of a is not all of a, so it's a proper ideal of a, and since m is a maximal ideal, the radical of a must be contained in m. Is that quite true? Because something tells me it could be the case that no, that's not true, because the radical of a and m, it's possible that these two ideals are not comparable. It could be the case that one is not that neither is contained in the other, and that's completely fine. When we say that an ideal is maximal, we mean that it contains, that there is any ideal that contains it must be either the maximal ideal itself or the entire ring. But that doesn't tell you anything about what happens if you have an ideal which overlaps with this maximal ideal a little bit, but not completely. Or rather, overlaps with some of the ideal, but not the rest. So let's draw a picture, because I like pictures. So let's say we have our maximal ideal m, and we have our ring A. So to say that m is maximal means that it cannot be the case that you have a ring A here in between. So if you have some ideal A in between m and A, then this fancy A must be either all of m, or this fancy A must be all of A. But what if you have an ideal A that's like this? Well, this is completely fine, because this fancy A ideal does not contain all of m, and so there's maximality doesn't tell you anything about this. This is completely legal. However, we do know something about the relationship between the radical of a and m. So 2 squared and t are both in a. So some power of 2 is in a, and some power of t is in a, i.e. 2 raised to the power of 2 and t raised to the power of 1. So that means that these two elements are contained in the radical of a. And if these two are contained in the radical of a, these are the generators of m. So m is the ideal generated by 2 and t. This ideal must be contained in the radical of a. And so now, we know that m is contained in the radical of a. Since the radical of a is not equal to a, the radical of a must equal m by maximality. Because the fact that the maximal ideal is contained in a proper ideal, namely radical of a, that necessarily implies that the radical of a must be this ideal m. So therefore the radical of a is equal to m. So now we want to prove that a is not equal to m to the n for any natural number n. Certainly a is not equal to m since 2 is in m but it's not in a. So then suppose you choose some n greater than or equal to 2, then t cannot be in m to the n. Because if you look at m to the n, what could something in m to the n possibly look like? Well, if you just look at like m to the 2, let's see here, m is generated by 2 and t. But if you look at m squared, then this could be generated by, well, you have to take two things in m and multiply them together. So the thing that's in the two things, so this will contain some a times b where a and b are both in m. So a and b, each of these could be generated by 2 and t. So at minimum, you could say that a is 2 or t or b is 2 or t. So you could basically say that m squared is the ideal generated by, you have 2 times 2, which is 4, then you have 2t, then you have t squared. And then you can keep going like this to get generators for, and like maybe some of these relations might be redundant, I don't really care, I'm not going to go into that much detail. But basically if you choose any n greater than or equal to 2, t can't be in there. Because how could t possibly be in there? Well, you'd have to take one of the elements. Basically, you'd have to write t as t times 1 times all the way up through times 1. And these you'd have n minus 1 copies of 1. Here, let me box this off to show that's different. So that's the only way you could get like t in m to the n. So certainly t is in m, so that's fine, but 1 is not in m. And there's really nothing else you could do here. Like, you'd think, oh, maybe you could like, well, 2 is in m, so maybe you could have a 2, and then, well, you'd have to multiply 1/2 to get back to 1 to cancel out that 2, but there is no 1/2 because these are all in integers. And you can't multiply by like t to a negative power, like t to the minus 1, because that's not inherent either. So there's no way to get t to be in m to the n. So therefore you have an element t which is in a but not in m to the n. So basically in all scenarios there's no way to, you can always find something that's in one but not the other, and so the two things can't be equal. Maybe there's a more elegant solution to this, but I think this one's like a very straightforward argument. Just like sort of getting your hands dirty with actual elements, which I am want to do because I like things to be a little more concrete, a little more tangible. But yeah, so there you have it. A cannot be m to the n for any natural number n, and we're done with this exercise.